Hello everybody, you're very welcome to this video. This is the third video in our sequence. I'm looking at financial maths, a very important part of our curriculum. In the first video we looked at long-term savings accounts. In the second video we looked at loans and mortgages, and in this video we're going to look at pension funds and how they work. So in the example that we've set up here, we're looking at a girl called Angela. Today is Angela's 25th birthday, so let's highlight the important parts of the question. So Angela is 25 years old today, and she's decided she wants to pay into a pension fund. She would like to retire on her 65th birthday. Now she's 25 today, she wants to retire when she's 65, so obviously there are 40 years in this pension fund. She decides to lodge €350 per month at an AER of 1.8 throughout the life of the pension fund. So she's got some kind of an agreement with the bank where they guarantee this 1.8% AER. So let's get going with this. First of all, they want to find the value of the fund on the day that she retires. Now, in our calculations, we're very simply looking at a situation where Angela is putting away €350 every month from now until retirement. So like the savings account in video number 1, in our savings video, we're looking at a situation where she's a regular saver. So the value of the fund is going to be 350. That's the amount that she's lodging every month. Now we're going to have to multiply that by 1 plus R to the power of the amount of time it's sitting in the account. Now, in case you're curious about why we multiply, remember we said you multiply by 1 plus R to the power of the amount of time if you feel that the fund is going to go up. Now Angela is 25 today and she wishes to retire when she's 65. So between now and then we're expecting this fund to grow. So that's why I'm multiplying. Now the interest rate that we've been quoted in the question is an annual interest rate, but we need to make payments monthly. So first thing that we need to do is we need to look at what 1 plus little r is. Now that's going to be 1.018. Now just to explain how I obtained that, I have got 1.8% the AER on the pension fund. Divide 1.8 by 100, you get 0.018, and then add 1. That gives you 1.018. Now that's annual, so we need to put that to the power of 1 over 12 to make it monthly. And that's going to give us a total of 1.001487765. Okay, and this is the value we're going to use for 1 plus little r for the rest of the first part of this question. So, remember what we said in the first video. If you feel that something is growing, you multiply by 1 plus r to the power of the amount of time. So this is 350 multiplied by 1.001487765 to the power of the amount of time that this is going to be sitting in the account. Now remember, Angela is 25 today, information given in the question, and she wants to retire when she's 65, which is 40 years away. So that particular payment is going to be sitting in the account for 40 years, which is 480 months. So that's going to be the power of 480. The next payment that Angela makes into the account is going to be in the account for 1 month less. So that's going to be 1.001487765 to the power of 479 because it's in there for 1 month less. And then this is going to continue on for the next 40 years. And then her final payment, so this is the last payment I'm looking at now, is going to be 350 multiplied by 1.001487765 to the power of the amount of time that that payment is going to be sitting in the account. Now, if we read the question carefully, we will see that the final lodgement up here is made 1 month prior to retirement. That's 1 month before Angela turns 65. So that's going to be to the power of 1, because clearly it's only going to gain interest for 1 month. Now we're in the exact same situation that we were in before. We take out our common 350. We can see we have a 350 in every term. And then we're going to reverse the order of the terms And that's purely so the powers rise instead of fall. It's just more visually appealing to see the powers rising instead of going down. So it's going to be 1.001487765 to the power of 1. You're reversing the order, so the last part goes first, plus 1.001487765 squared, because remember you're reversing, so now the powers are going up, and then plus 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 all the way until the very last one, which is going to be 1.001487765 to the power of 480. Remember, we are reversing the order of the powers, so 480 was first, it's now last. Okay, we reverse the order of the powers. Now, as in all of these questions, or most of the questions that we've done, we now notice that inside here in our curly brackets, we have a geometric series. Okay, now it's a geometric series with the first term equal to 1.001487765. And you'll notice that that's also the number that we're multiplying by every time when we move from one term to the next. So the common ratio, remember we use capital R for the common ratio and small r for the decimalized interest rate. So capital R and the first term are both the same number, 1.001487765. Now, again, as in the previous videos, I would now advise you to pause for a minute and just think about your common ratio. This is a pension fund for Angela before she retires, and during this period we will be expecting the fund to be increasing. So therefore we would expect a common ratio larger than 1. So I'm very, very happy that that common ratio is bigger than 1. Now, the formula that we use to calculate the sum of that series is Sn equals A into r to the power of n minus 1 divided by r minus 1. Remember, I have reversed the formula that's in the log tables because in this case, our common ratio is larger than 1. Okay? Now, so getting back to our calculations for Angela's pension, we now have the 350 from here. So that's 350 multiplied by the sum of 480 terms. It's very, very clear that we're starting counting at 1, 2, 3, 4, 5, 6, all the way up to 480. So there are 480 individual payments into this pension fund. So there are 480 terms in our geometric series. Now, on the next line, we simply use the formula that we have over here on the right-hand side to calculate S480. So this is 350 multiplied by little a, which is this number here. So multiplied by 1.001487765. Then multiplied by r to the power of n inside in the brackets. So that's going to be 1.001487765 to the power of the number of payments which are made, the number of terms in our series, which is 480, minus 1, and then divided by the common ratio minus 1. And that's going to be 1.001487765 minus 1. Okay? Now, on the next line, it is simply just using your calculator, and we can see that the value of the fund, when we've put all of those numbers into our calculator, is going to be €245,337.25. Now, that's why the banks always encourage us to start pension funds early, because on the day that we retire, everybody wants to have a large pot in their pension, but it takes time to build up that pot. And because it takes so much time to build up the pot, it's good to start the pension fund as early as possible. So that is the value of the fund on the day that this lady, Angela, retires when she's 65 on her 65th birthday. So up until she retires, Angela is paying into this fund. She is a regular saver. Now, obviously in part 2, we're going to look at the situation after Angela has retired. So now she's going to be taking money back out of this pot, okay, at a given rate. So let's read the next part of the question. As stated in part 1, Angela is due to retire on her 65th birthday. If the fund accumulated in part 1, so that's 245,000, etc., is to be given back to Angela after retirement in equal monthly payments. So she's to get this back in equal monthly payments. Now that's very, very important. Find the value of these monthly payments subject to the following conditions. She receives her first payment 1 month after she retires. So that's 1 month after her 65th birthday. And the last on her 80th birthday. Okay, so the good news is that for Leaving Cert pension fund questions, they have to put a start date and a finish date so that we can actually do the calculations. So the payments start 1 month after her 65th birthday and they end on her 80th birthday, and they're monthly payments. And at this stage, the value of the fund is 0. So that is on her 80th birthday. Okay, so she's nominally left after that time. And we're told that the AER is 1.8%, just as it was in part 1 of the question. Okay? Right. Now, first of all, we know a certain amount of information from before. Because the interest rate is the same, 1 plus little r is still 1.0014877765, just as it was in part 1. And here's a very important point. After Angela retires, the value of her fund starts to decrease. Okay, once she starts to take money out of it, her fund is decreasing. Now remember, you multiply by 1 plus r when a fund is increasing, and you divide by 1 plus r to the power of whatever the amount of time is after when it's decreasing. Okay, so you multiply until Angela retires, and then you divide after retirement, because from that point on, the fund is decreasing. So the value of her fund from the previous part, which was €245,337.25, is going to be equal to the sum of the present values of all future payments which Angela receives from her pension. Now that's extremely important. It's the sum of the present values of all future payments which she receives from her pension fund. Now we're going to imagine that these equal monthly payments are of size €1. Because the fund is going to decrease, we know we should be dividing. So the first payment that Angela receives is 1 month after she retires. So that's going to be A divided by, remember, decreasing, divide, increasing, multiply. But this is decreasing, so we divide by 1.00, etc., to the power of the amount of time which has passed since retirement. Remember, this was the value of the fund on retirement day, so that everything is referenced back to the day that she retires. So that's to the power of 1, because she receives her first payment 1 month after she retires. The next one is A divided by 1.00 1487765 squared. That's because that's a month later. So 2 months have passed since the day that Angela retired. And then this continues on until she receives her last payment, which according to the question is on her 80th birthday. So that's going to be 1.001487765 to the power of the amount of time which has passed in months until she's 80. Now, from 65 to 80 is 15 years. There are 12 months in every year. So 15 multiplied by 12 is 180 months. So 180 is 15 years multiplied by 12 months. Now, just as we had in our loans and mortgages section, we now do the exact same thing as before. We take out that common A, and also, because we don't like fractions, I'm going to actually calculate what this number is. Okay, 1 over 1.001487765. Now, I'm purely doing this just to avoid fractions. Now, when I do that calculation, I get 0.998514444 and then a 7 tagging on at the end. Okay, and this is just literally to avoid fractions, all right, which I think most people would like to do. So now, instead of this one, we put in 0.998514447 to the power of 1 plus 0.998514447 squared plus ... all the way until the end of our pension, which is 0.998514447 to the power of 180. That's at the end of the life of her pension when she's 80 years old. Okay? Now that means that 245,337.25 equals A multiplied by the sum of the first 180 terms of the geometric series. I hope everybody can see that inside in here, in the curly brackets, we again have a geometric series where the first term is 0.998514447, and the common ratio is also the same number. As always, we pause for a second just to double check our common ratio makes sense. This is after Angela has retired, so it makes perfect sense that the common ratio is smaller than 1, because after retirement she would clearly expect that her pension fund is going to decrease in value. So hence we're quite happy that that's smaller than 1. Now, Sn in this case, we're going to directly use the formula which is in the log tables. 1 minus r to the power of n over 1 minus r, and we're using that because r is less than 1. Now remember, in the first part of the question, we used the r greater than 1 version of that, which was literally just swapping the signs on the top and the bottom of that fraction. Okay, so on the next line then, we literally just put the numbers into the formula. So what we have next is that 245,337.25 equals capital A multiplied by small a, which is 0.998514447 into 1 minus r to the power of n, which is 0.998514447 to the power of the number of terms, which is 180. And then that's all to be divided by 1 minus 0.998514447. This point, it's just calculator work again. So we simply grab our calculators and we work out what everything inside this red curve is. Okay? Now when we calculate that, we get 245,337 euro 25 cent equals the monthly payments capital A multiplied by 157.8106627. So all that's left now is a matter of dividing across by 157.8106627. So the monthly payments capital A is 245,337.25 divided by 157.8106627. And that's going to give us a value of €1,554.63 per month during her retirement. So I hope you understand all of the calculations in that. The beauty of the pension question is that it has both sides of the coin. It has a regular saver until the day that you retire, and then it has something similar to a loan. Obviously a pension is not a loan, but it's quite similar to a loan after the retirement day. So I would again strongly advise that you have a look at this video several times until you understand exactly how pension funds work. So I hope you enjoyed the video. Please keep track on the channel, and further videos will appear of different things that you may be interested in me doing. Thanks very much. Bye-bye now. Bye-bye.